Hello, in this video we're going to be talking about mass, moments, centers of mass, and centroids. So first let's talk about mass. If we have a 3D object with a simple shape and a constant density, mass per volume, then we can find the mass of the object just using precalculus. Basically just figure out the volume and multiply by that density. However, if the shape is complicated, or if the density is variable, or both, then we need to use integral calculus to figure this out. Once again, the basic definite integral application approach is used. The idea is to divide up the region into small little parts, approximate the mass of the little part by assuming it is a simple shape with a constant density and using precalculus. Sum these approximations and then take a limit to turn it into an integral. So let's look at this example. Let's find the mass of a column of air. Suppose the density of air at height h meters above the Earth's surface decays exponentially at a rate of 0.000124 per meter. Okay. Furthermore, the density of the air at the surface is 1.28 kilograms per meter cubed. Find the mass of a cylindrical column of air 2 meters in diameter and 25 kilometers high. So here what we want to do is make little slices at a constant height. Since the shape is a right circular cylinder, both of the column and the slices are little circular discs, a simple shape to find the volume of. However, we have variable density. So this is going to force us to use an integral. Now, since the density of air decays exponentially, we see the density is given by a following formula. Rho of h is the height above ground, is rho sub 0 times 1 plus r to the h. That's the basic formula for an exponential function. The rate of decay was 0.00124, so r is negative 0.00124. And the initial value at height 0 is 1.28. And of course the units here are kilogram per meter cubed. We need the height in meters. Doing this subtraction right here, you get 0.999876. Although it's not necessary, I'll put those zeros in there to make that a little bit easier to read. Notice that it did not say this was an exponential or continuous rate, so it's not e to the negative 0.000124. h, which would it be if it said exponential rate. Since it is decaying, the r is negative. We take a representative horizontal strip at a constant height in the shape of a disk, and we compute its volume. Well, the volume is pi r squared, the radius of the disk, is r. The height is some dh. Well, the radius was, it was 2 meters in diameter, so that's 1 meter in radius. So it's just pi dh is the volume. And that, of course, would be in cubic meters. And notice that the height of the cylinder is 25 kilometers, which is 25,000 meters. To compute the total mass, we evaluate the following integral to see if the mass is going to turn out to be 31,000 kilograms to 3 significant digits. I'll end up rounding to 3 significant digits since the data given was rounded to 3 digits. That's 3 digits there. If we assume those are exact values, then this is still 3 digits here. So we got it, at the best, we're going to get 3 digits on our answer of accuracy. So all you have to do is just integrate the rho times the volume. And the volume is going to be, again, it's going to be pi dh, and then the rho is given by the 1.28 times this 0.999876. Okay, so let's see. I can pull the pi and the 1.28 out front. We have this. Actually, it's not too hard to do a very simple antiderivative. It's just the same function, but divided by the log of the base, which is what I have there. Evaluate from 0 to here. When you put in the 0, that becomes 1, and then that is some number there. Okay, so there it is, which is approximately this to the limits of my calculator, or approximately 31,000 kilograms, and that's to the nearest 100 kilograms, rounded off to 3 significant digits. All right, what about this situation? So let's just back up and think about what we did there. We had a nice shape, but variable density. Okay. Here's another one. We have a rod with varying density. We institute a coordinate system at one end of the rod, putting the other end at 10 on the x-axis. So the rod runs from 0 to 10. The density is given by rho of x equals 10 sine of pi x over 10, and that's really per linear. That's like some mass per linear unit. And find the mass of the rod. Well, we just integrate that density from 0 to 10 to get the mass. Okay. And I didn't put any particular units in it, but something that might be appropriate would be x might be in meters, the density might be in actually in say kilograms per meter. This time, right? Assuming some constant cross section. So in any event, we're just integrating that function. So if we put pi over 10 here, this is sine of u du. We balance by putting 10 over pi with that 10 makes 100 over pi out front. So it's sine u du. Antiderivative would be minus cosine of u. So we got a minus 100 over pi cosine, evaluated from 0 to 10. 10 over 10 is 1. Cosine of pi is there. This is cosine of 0. Cosine of 0 is 1. Cosine of pi is negative 1. Two negative 1s make negative 2. Makes that positive and makes that 200. So the final answer is 200 over pi, or about 63.661977. So we have a density. Kind of a strange rod because actually it's going to hit 0 density at a few places along the way, but at least in theory, the basic idea there. Now, some other applications work essentially the same as computing masses. Anything that has a rate per area or a rate per volume or even a rate per length works essentially the same way. For example, the following exercise, we're given the population density, and we can compute from that the total population. Suppose there's a circular shaped city in the middle of a desert. Like most cities, its population is denser in the center and thins out as you near the city limits. In fact, let's assume its density is given by 10,000 times 3 minus r people per square mile at a distance r miles from the center of the city. Being in the desert, its population is 0 at the city limits, which are, as you can see, are 3 miles out. So the density is 0 when r is 3, so the city has a radius of 3 miles. We take a representative piece to be an annular ring, like a washer, with an average radius r and a thickness dr. So the area of the piece is 2 pi r dr. Multiplying this by the density and integrate to find the population. That area, remember, we figured this out when we did the washer method, that's what it would be. So it's 2 pi r dr. So 2 pi r dr times the density. The density was is changed. So the shape is relatively simple. It's an annular ring or a washer, but the density is variable there. So we need some calculus here. So what did I do here? I factored the 1,000 out and the 2 out and the pi out. So I got 2,000 pi out front. That leaves me 3, and I distributed r. So 3r minus r squared. Oh, that's not hard to do. Let's see. We just add 1 to the power, divide by the new power. So that's r squared divided by 2 is 3 halves. R cubed when you add 1 there, so that's 1/3 there. Still got our 2,000 pi out front. Evaluate from 0 to 3. I'm going to get rid of the fractions here by factoring out a 1/6. 1/6 leaves a 3 in the denominator here. The 2 cancels that down to 1,000. And we're factoring a 1/6. This means we're going to essentially multiply by 6 here. Multiplying by 6 cancels the 2 to the 3 times 3 is 9. So we got 9r squared. And then 6 times 1/3 is 2. So that's a minus 2r cubed. Now evaluate from 0 to 3. We put in the 3, plug in the 0, and evaluate. The zeros work out to be zeros. 3 squared is 9 times 9 is 81. 3 cubed is 27 times negative 2 is negative 54. 81 minus 54 is 27. Right? Yeah. 27 divided by 3 is 9 times 1,000 pi is 9,000 pi. So the answer is 9,000 pi, or approximately 28,274.334. This is people, so we'd round off, certainly round off at least a whole number. In fact, it was not clear how many significant digits we had. But let's say we've got a couple of significant digits here, so about 28,000 people. Okay, let's continue on. Let's keep talking about the center of mass. The center of mass is the point that an object would balance. You know what? I'm going to stop the video here. We're going to come back at the next video for this one.